Welcome everybody to another Gauss Slab problem, and today we'll be dealing with a square insulating slab that is 5 millimeters in thickness and that is 2 by 2 in length and height, and it has a charge of 8 times 10 to the negative 11 coulombs distributed uniformly throughout its volume, and we have to find the electric field at point P beneath 1 millimeter of one of its faces. So like any other Gauss slab problem, a good place to start is to start with a diagram. Even though we're already given one, it's always good to make your own. So here we have the front face of the slab, and the slab goes off in this direction. Like connect there, and I'm gonna go ahead and draw the center line for the slab. There we go. So this is the center, and this is point P. So point P is 1 millimeter below the surface. So it's 1 milliliters here, 1 millimeter downwards, meaning that it has to be 1.5 millimeters from the center, because 1 millimeter plus 1.5 millimeters is equal to 2.5 millimeters, which is half of 5 millimeters. So it is 1.5 millimeters from the center. And we want our Gaussian surface to just touch this portion, touch the point on one of its edges. So our Gaussian surface should also be a square, or a square that is 1.5 millimeters in length and 1.5 milliliters in height. So our Gaussian surface should look something like this. Okay, and because our Gaussian surface is a square, the area of our Gaussian surface is just going to be 1.5 millimeters times 1.5 millimeters. Fairly simple. And since we established our Gaussian surface, we can go ahead and use Gauss's law equation, which is E times A is equal to Q enclosed over epsilon naught. Well, we already talked about how E of how A is going to be 1.5 millimeters, which I'm going to change to 1.5 times 10 to the negative 3 meters times 1.5 times 10 to the negative 3 meters. And this is going to be equal to Q enclosed. So what is Q enclosed? Since we're dealing with an insulator here, the Q enclosed is going to be the ratio of the volumes between the total volume of the slab versus just the volume of every Gaussian surface. And because every Gaussian surface is pretty much just a cube, our Gaussian surface is going to have the volume, or the volume that we used, which is the volume of our Gaussian surface. It's just going to be 1.5. No. Oh, let me just fix that real quick. It's just going to be 1.5. There we go. Hello, like that. Small eraser. There we go. Sorry about that. It's just going to be 1.5 cubed, because that's the times 10 to the negative 3 meters cubed, because that is the volume of a cube, and the volume total is going to be 0.5 from right here. So 5.0 times 10 to the negative 3 meters times 2 meters and times another 2 meters. So times 4 meters squared. So the ratio is going to be 1.5 times 10 to the negative 3 meters cubed over 5.0 times 10 to the negative 3 meters times 4 meters squared. And this entire ratio is going to be multiplied by our total charge, which is 8.0 times 10 to the negative 11 coulombs. So we get the charge just for our Gaussian surface. And this is going to be all divided by epsilon naught. And you can see that we have some great constellation here. These two go away with two of those, leaving just one of these. And then you have E by itself. So after putting this into a calculator, E will equal simply 0.68 newtons per coulomb. So for every coulomb, the electric field is going to exhibit 0.68 newtons of force. So that's how you find the uh, electric field of a insulating slab. And I'll see you in the next video.